everyone, and welcome to another video. Today I'd like to kick off a three-part series focusing on introductory wind tunnel testing. So here's the roadmap for the series. Today I'd like to introduce the concept of wind tunnel testing and focus on data acquisition. So in other words, how can we leverage a wind tunnel to obtain raw aerodynamic data? So we will accomplish this by taking an in-depth look at one of the best university wind tunnels in the country, namely the Kirsten wind tunnel at the University of Washington. We'll take a virtual tour of the wind tunnel and talk about the various systems and instruments that are used to acquire raw aerodynamic data. Now, once we understand how a wind tunnel works and how we acquire raw data, in part 2 of the series, we'll look at the data reduction process that is used to transform this raw data into data that better represents a full-scale aircraft. Finally, in part 3 of the series, we will focus on looking and analyzing the resulting data, as well as discuss some other considerations for wind tunnel testing. So, if that sounds like fun, let's jump over to the slides and get started.
So at a high level, the primary goal of conducting a wind tunnel test is to try and understand how a given aircraft will perform in different aerodynamic conditions. More specifically, if you're given an aircraft geometry, we'd like to characterize how the aerodynamic forces and aerodynamic moments are a function of the states and controls. So, for example, perhaps we would like to know how much lift is generated when the angle of attack is, positive 2.5 degrees, the airspeed is 150 miles an hour, and the elevator is deflected by -1 degrees. Now, we could go to a wind tunnel and recreate these desired aerodynamic conditions and then simply measure the amount of lift that's on the aircraft. Now, keep in mind that lift is only a single component of the force vector acting on the aircraft. What about the drag and side force? Now, furthermore, what about the aerodynamic moments? We should probably also measure the pitching, rolling, and yawing moments about the aircraft's center of gravity at this aerodynamic condition. Now, how do these aerodynamic forces and moments change if we were to, say, change the aerodynamic conditions? So, for example, what if the angle of attack was 3 degrees instead of 2.5? And now, what if we also deflect the rudder? So, as you can see, there are a ton of data that is collected during a wind tunnel test with the ultimate goal of trying to characterize how do the aerodynamic forces and moments change as a function of the states, which I'm denoting here as X, and the controls, which I'm denoting here as U. So, the states could be things, again, like angle of attack, angle of side slip, dynamic pressure, Mach number, etc. And the controls could be all kinds of different things like the ailerons, the elevators, the flaps, etc. So you can see that it's a fairly complicated process with a lot of different variables being measured and a lot of different variables being changed. Now, it's also worth mentioning right here that most wind tunnels are great for obtaining the static dependencies. In other words, how are these forces and moments a function of constant or steady state flight conditions? So, if you're an aerospace engineer, I'm sure you know that there are some aerodynamic forces and moments which you might be able to dynamically change. For example, you might be able to temporarily get an increase in lift if you perform a, kind of a dynamic pitch nose-up maneuver. However, most wind tunnels are set up to hold the model of the aircraft steady and then acquire data. So attempting to characterize dynamic aerodynamic forces and moments is typically not practical in a wind tunnel. So that was what we want to do. How are we going to do this? So again, at a high level, conducting a wind tunnel test is actually fairly straightforward. So let's start with the aircraft. Now, as you can imagine, a full-scale aircraft is too big to fit in most wind tunnels, so we're going to need to create a scaled-down aircraft model. We can then mount this aircraft to a balance, which is just an instrument that's used to measure forces and moments. We can then use a fan to blow air over the model to generate aerodynamic forces and moments, and once we're on condition at the appropriate orientation and wind speed, we can just gather and record data from the balance. Now that we have a general idea of why wind tunnels are useful and how to acquire data, I'd like to take an in-depth look at a specific wind tunnel, namely the Kirsten wind tunnel at the University of Washington. The Kirsten wind tunnel is a subsonic wind tunnel and part of the William E. Boeing Department of Aeronautics and Astronautics. So it was built in 1936, and interestingly, it operates as both a research laboratory and a commercial test facility. So it's led by a staff engineer/manager as well as a crew of student employees. And actually, as a fun fact, I worked here for over 3 years in the early 2000s when I was a student at the UW. And as such, even though there are bigger, faster, and newer tunnels, this one is always going to be my favorite. Here are some general tunnel specifications. So you can see it can generate wind speeds of up to around 200 miles an hour, which is roughly a dynamic pressure of around 100 pounds per square foot. The test section is 12 feet wide by 8 feet tall by 10 feet long, and the balance is rated for up to 2,500 pounds in lift, 250 pounds in drag and side force, and 5,000 inch-pounds in roll, pitch, and yaw. Now, the tunnel actually has a unique closed-circuit double return design. So this means that there are two fans which push air around in a closed loop. So the wind actually makes two 90-degree turns before accelerating through the bell mouth, going down the test section, and then decelerating in the diffuser before making another two 90-degree turns to return to the fans. So at this point, I'd like to take a closer look at various areas of the Kirsten wind tunnel. We'll start with a small intro video and then head to the ground floor before moving up to the fan decks where we'll see the motors and fan blades that generate the wind. We'll then go over to the model deck, which is where you can enter and exit the test section. Once we see how the model's mounted, we'll actually go below the test section to the balance deck to see where the balance is located, which is the real heart of the tunnel. We'll then show the traverse deck, which is on top of the test section, before going into the control room to see where the tunnel is controlled from and how we gather data. So to do this, we're actually going to view a series of older historical videos that document some of these areas. These videos are a bit old and lower resolution, and some of the information might be outdated, but I think they're fun to watch and informative nevertheless. These videos were actually generated by my good friend and colleague Andrew McComas, who I actually worked with at the Kirsten wind tunnel back in the day. So, without further ado, let's head over to the tunnel. For some reason, the audio from these original videos were somewhat garbled, so I'm going to try and do a voiceover of some of the original commentary of these videos. Welcome to the University of Washington Kirsten Wind Tunnel, also known as UWall. This program will take you through the Kirsten Wind Tunnel, located at the heart of the University of Washington campus. Along the way, you'll be presented with some of the history of our building, along with many of the services that the tunnel currently offers. The Kirsten Wind Tunnel is a closed-circuit double-return wind tunnel. Two fans located in the circuits on either side of the test section can simultaneously generate wind reaching 200 miles per hour. The wind moves around the corners with the help of curved turning vanes. It is then straightened and funneled through the bell mouth ahead of the test section, thereby increasing the wind speed 6 times. After passing through the test section, the wind slows down, passing through the diffuser for its return trip to the fans. The overall momentum of the wind is conserved, giving the tunnel a dramatic power advantage over open-circuit tunnels where the wind is vented to the outside. The building was the idea of Frederick Kirsten, who taught as a professor of aeronautics here at the university from 1915 to 1951. Construction of the wind tunnel began in 1935 and was completed in 1936. At this time, calibration of the tunnel's flow characteristics were performed prior to the first public test in 1939. The building is comprised of brick and concrete and has 3 main levels. On the ground floor is the loading bay where the drive system, auxiliary motor generator, calibration model, and vehicle ground plane are located. Also on this floor is the model shop where you'll see all the model preparation area, tools, and data storage vault. Going up to the second level are the fan decks, test section, model deck, balance deck, and observation deck. On the top floor are the traverse deck, control room, and customer room. Here's where the tunnel operator's console, the data acquisition and reduction station, and the customer offices are located. The ground floor is a primary access point to the rest of the tunnel. Located here are tables for model preparation and temporary storage. During model installation and removal, the model is wheeled into the ground floor area just below the observation deck. The observation deck's floors are lifted out of the way and the model is hoisted to the ceiling for installation in the test section. The model shop is also located on the ground floor and has plenty of floor space for model preparation and alteration. The shop is furnished with a bandsaw, drill press, belt sander, standard hand tools, and a precision surface table. The shop is available for the customer's use throughout the test. A fully furnished machine shop is available in an adjacent building for more elaborate machining needs. Completed test data is archived in a Class 6 U.S. government security vault located in the shop. Records from tests dating back to the 30s remain in our vault to this day. The tunnel is powered by 2 variable speed 500 horsepower direct current electric motors located on the fan decks. The wind speed is controlled by varying the electric current to the motors, thus adjusting the motor RPM. The electricity is supplied by a solid-state 12-pulse DC drive capable of outputting up to 600 volts with less than a tenth of a volt resolution. These motors power two custom-designed 7-bladed fans. The designers of these fan blades chose Honduras mahogany for its excellent fatigue and fracture characteristics. Each fan is 14 feet 9 inches in diameter with a quarter-inch gap between the blade tip and the wall. The loading bay is used for loading and unloading of models tested in the wind tunnel. It's also used for long-term storage of large items such as the vehicle ground plane and calibration model. Our calibration model is installed and tested once a year to ensure the repeatability of our data. The Kirsten wind tunnel has an auxiliary motor generator for powering models with moving propellers or motors. Like our main fan motors, the model motors are controlled remotely by the tunnel operator. I just wanted to interject some commentary about the fans. Here's a better picture of one of the fans to give you an idea of the size. So as you can see, there are 7 blades on each set, and the diameter is about 14 feet 9 inches. I'd also like to call your attention to the clearance between the tips and the walls. So there's only about a quarter-inch clearance. So this is done to reduce the effect of tip vortices coming off each of the blades and therefore keeping the flow as smooth as possible. However, this can actually be a little bit dangerous because a part that dislodges from the model and makes its way back to the fans can actually get wedged between the fan and the wall. So, interestingly, if you ever get a chance to see the fans up close, be sure to look at the walls near the blades and you'll actually see some chunks of concrete that are missing from the wall where there have been tip strikes in the past. One of our jobs at the tunnel was walking around the entire circuit and checking for FOD on the floor to make sure that when we fired up the tunnel in the morning, a loose nut or bolt wouldn't get sucked back here to the fans. And as you can see from the diagram on the right, there are 2 mirror image sets of motors and fans. As the video mentioned, each fan is powered by a 500 horsepower DC electric motor, and the fan motor armatures are actually linked by an idler shaft to ensure that both fans spin at the same RPM. Okay, so enough of my commentary. Let's jump back to the videos. The model deck, located adjacent to the test section, is designed for minor model work and assembly and contains commonly used supplies such as various tapes, screws, files, glues, and putties. Hand and power tools, compressed air, and plenty of space is provided to accommodate model changes. The test section is accessed through 2 doors on the model deck. The test section is 8 feet high, 12 feet wide, and 10 feet long, with fillets on all corners. The test section is vented to the atmosphere to keep the static pressure inside approximately equal to the ambient air. The lighting in the test section can be controlled to provide proper conditions for high-speed photography or other needs. The floor is made of removable aluminum plates that can be replaced with viewing windows to allow for observing the underside of the model. The model can also be viewed through interchangeable windows on the test section ceiling. Models are installed by opening the ceiling. Aircraft models are mounted to a strut similar to the one seen here. The strut assembly is connected directly through the floor to the balance below. The outer fairing is connected to the floor and does not touch the strut. Inside the balance is a motor that rotates the strut to yaw the model. An arm on the strut is moved vertically to pitch the model. Again, I just want to provide some additional commentary about the test section. Obviously, aircraft are the most popular thing to test in the wind tunnel, but the same concept can really be applied to anything that's subjected to aerodynamic forces. So, for example, cars and trucks are a popular non-aerospace item to test in wind tunnels. In fact, this right here is a full-size Formula SAE car built by the UW Formula Motorsports team and installed in the wind tunnel for a test. We've also tested things like bikes and tents and a lot of other items that are not traditionally linked to aerospace. The balance deck, located directly underneath the test section floor, is home to the Kirsten wind tunnel external balance and pressure system. This original design balance has been in use at the tunnel since the first public test in 1939. The balance simultaneously measures the 6 forces and moments acting on the test object, namely lift, drag, and side force, and pitching, yawing, and rolling moments. These forces and moments are converted to voltages through a series of electromagnetic servo force balances. These are known as Eastman pots and were designed by Fred Eastman in the early 1930s specifically for our wind tunnel. The output voltages are then measured by our data acquisition computer and converted to engineering units of pounds and inch pounds, which are saved on the Kirsten wind tunnel computer network. The Kirsten wind tunnel is also capable of measuring pressure data. Pressure tubes can be routed to small holes on the surface of the model from an electronic pressure scanning system, or EPS, which monitors the individual pressures. The EPS has a capability of measuring up to 1,024 separate pressures simultaneously. The traverse deck is located directly above the test section and contains much of the hardware for flow visualization processes. The test section ceiling is on tracks and can be moved sideways across the tunnel by an electric motor. The carriage located on the test section ceiling supports 2 struts which can be driven on vertical tracks. This allows for accurate 3-axis positioning anywhere in the test section of probes mounted to the end of these struts. The control room is located on the top level of the building. From here, the tunnel is operated, data are acquired and reduced, and the test is monitored. The Tunnel Operator's Console, or TCAM, has controls for operating the tunnel, changing wind speed, adjusting model position, and acquiring data. Online plots of corrected coefficient data are available immediately after a data point is acquired. Real-time plotting is available for all PCs on the Kirsten wind tunnel network. The test engineer can specify the test variables on the run board across from TCAM. The tunnel operator will then reference this board for instructions and test documentation. The crew applies specific corrections to the raw data during the final data reduction process. Data is typically corrected using an in-house software package written in Visual Basic. Final data, digital images, and digital video are provided to the customer at the end of the test on DVDs. A customer room is located adjacent to the control room to provide a convenient office for the customer while testing. The customer room has 5 desks with 5 computers connected to the Kirsten wind tunnel network and a door that can be closed for privacy. It also has an exclusive telephone line dedicated for customer use. Okay, now that we've seen what a wind tunnel looks like, let's talk about the data acquisition process. When I say data acquisition, I mean the set of procedures used to obtain aerodynamic data for the aircraft under test. As we discussed previously, the wind tunnel is used to measure aerodynamic forces and moments acting on the aircraft. For the sake of completeness, here are the sign conventions that most wind tunnels use for positive quantities such as lift, drag, and side force, along with the rolling, pitching, and yawing moments, angle of attack, and angle of side slip. Keep this in mind as they'll be relevant during part 2 of our discussion when we investigate the data reduction process. While we're talking about aerodynamic moments, it's also relevant to look at this diagram. I want to mention that the balance will measure and report moments about the balance moment center, which is a virtual point in the test section. In the case of the Kirsten wind tunnel, this location is exactly in the center of the test section. Usually, this location doesn't align with the desired center of gravity of the aircraft, so these moments are going to need to be transferred to a specified model moment center. Again, I just wanted to briefly talk about this to put the idea in your head that we're going to need to perform some type of manipulation and transformation on the data that we acquire from the wind tunnel. So, finally, let's talk about the procedure for acquiring data in the wind tunnel. First, we saw that the balance is simply an instrument that outputs voltages proportional to the applied loads on the model. The mapping between the raw output voltages and the actual engineering units of pounds force or inch pounds force must first be completed before we take data. Assuming this has been completed, we're now ready to take aerodynamic data. The first step in this process is called a wind off zero, or a WOZ. This basically means taking a data point when the wind is off and then subtracting this value from all subsequent data. The idea is that when the wind is off, there should be 0 aerodynamic forces and moments, so any non-zero values that the balance is reading are just noise and they need to be removed. This is effectively the same thing as tearing out your scale before using it. Once the WOZ is complete, we bring the wind up to the desired airspeed, or more commonly referred to as the desired dynamic pressure, or Q. Now, once the wind when the wind is being brought up, what we'll also do is simultaneously pitch and yaw the model to the desired orientation. Now, once the wind and orientation of the model is correct, we'll start to take data. We sample all the relevant channels at 100 Hz and collect 5 seconds worth of data. Note that we only take data when the wind is within 1% of the desired condition. We then use this to create an averaged data point and save all of the relevant variables. Now, this is the procedure for a single data point. We can then repeat steps 3 through 6 for different aerodynamic conditions. So for example, it's common to hold the angle of side slip constant and then vary the angle of attack through a range of values. So this is sometimes referred to as an alpha sweep. Now, a single alpha sweep might contain 10 or 20 data points. After you finish an alpha sweep, you might want to change the angle of side slip and then repeat the same alpha sweep. And once you've collected a family of alpha sweeps for a given configuration, you'll probably need to bring the wind down so that the technicians can go into the test section and perform a model change. So for example, you might want to try out a different tail or change the angle of a control surface. And then you get to repeat the entire process again. So, as you can see, if you want to cover a large portion of the operating envelope with multiple different configurations, this has the potential to generate huge amounts of data, which can take huge amounts of time and money to collect. Part of being a good test engineer is identifying conditions that are critical and getting good data for these configurations, and then ignoring or skimping on other less critical configurations in order to optimize your entire test matrix. Again, keep in mind that this is the procedure we use to obtain force and moment data. I want to shift gears slightly now and talk a little bit about different types of data that you can acquire during a wind tunnel test. In addition to aerodynamic force and moment data, there's actually a lot more information and data that can be gathered during a wind tunnel test. One class of data is known as flow visualization, or FlowViz. So these are techniques that are used to attempt to literally visualize or see what the flow around the aircraft is doing. One of the easiest ways to do this is known as smoke flow visualization. So here we introduce smoke into the airstream and see how it behaves around the model. This is really useful for helping estimate things like boundary layer thickness or observing other off-body flow field characteristics. Conversely, if you want to understand how the flow on the body is behaving, you can use techniques such as polybutene oil spots. So these are dots of viscous oil that you place on the model when the wind is off. When you bring the wind up, the oil runs in the direction of the streamlines and helps you visualize the flow field on the aircraft. A related technique is the China clay method. China clay is actually a mixture of kerosene and day-glow powder. The idea is you paint or spray this mixture onto the model and then exit the test section and bring the wind up. Similar to the oil, the China clay will flow in the direction of the streamlines, and if you leave the wind on long enough, the kerosene will eventually evaporate, leaving the day-glow deposits in the flow pattern for that particular configuration. It generates beautiful images that are very helpful for visualizing the flow field. A third technique of on-body flow visualization is known as tufting or tufts. In general, this means to attach tiny strings to the model, which again will be deflected in the direction of the streamlines. The trick is to make the tufts as small as possible so you don't influence the flow field. The problem is that the smaller you make the tufts, the harder they are to see. So one way around this is to use what are called fluorescent mini tufts. These are small filaments of polyester monofilament that are soaked in an ultraviolet dye and then glued to the model surface. When the wind is turned on, the mini tufts move in the direction of the flow, and a UV flash is used to make the tufts visible. This works surprisingly well, but unfortunately it can take a significant amount of time to apply these tufts to the model. Continuing with our topic of non-standard data that you can acquire in a wind tunnel test, a very popular option is acquiring pressure data on a model. So this involves using an electronic pressure scanning system, or EPS, to measure the static or total pressure at various locations on the model. Now, often this means installing lots of little pressure ports all over the model, and this can be a pain to install and wire all these ports. In fact, this is a picture I took with some of my colleagues at UIUC when we were, I think we spent, must have been 3 days of wiring hundreds of these ports onto this model wing that we were testing. However, if you get through all of that pain, it lets you measure the static pressure over the entire model, and if you integrate and combine this with the geometry of the wing or the model, you can actually get local lift and drag distributions along the model, as well as create some really cool plots. Now, the pressure taps that I showed in the previous slide were part of a large multi-year project that we were conducting in collaboration with several partners such as the FAA, NASA, and UIUC, to name a few. The goal of this project was to characterize how ice accretions on a swept wing affected the aerodynamic performance. I wanted to take a moment to talk about a really cool wind tunnel, the NASA Glenn Icing Research Tunnel, or IRT. Now, this is literally a wind tunnel inside a giant freezer. So this lets us actually grow ice accretions on a swept wing in representative aerodynamic conditions. We then laser scan these ice accretions and 3D print plastic versions of the ice that we could then test in normal wind tunnels such as the Walter H. Beach Memorial Wind Tunnel in Wichita, Kansas, or the pressurized Onera F1 tunnel in Toulouse, France. I just wanted to throw in this because it's a really neat capability and shows off another dimension of wind tunnel testing that you typically don't think about. If you're interested in the details of this test, feel free to check out these two papers listed here on the side. Now, as part of that same icing project, we employed a technique to survey the wake of the model to understand how these ice accretions affected the downstream flow field. So in this case, we used an array of 3 probes. Now, each of these probes have 5 holes, so they're sometimes referred to as a 5-hole probe. And what that does is each one of these 5-hole probes is able to measure the total pressure and the entire velocity vector, both magnitude and direction, of the flow at its tip. So what we did is we swept this array behind the model to try to map the entire wake of the model, and then we would do this at a certain angle of attack, change the angle of attack of the wing, do it again. This allowed us to look at how the wake changes as a function of angle of attack, as you can see in this bottom movie. Again, this data shows some really interesting phenomena. For example, if you look at the top figure where I'm plotting the local velocity vectors, you can clearly see the tip vortex and how the distribution of downwash varies across the span of the wing. You can think of the wake survey as basically another type of flow visualization, but as you can see, you get a lot more information than some of the more simple techniques such as China clay or tufts. Again, if you're interested in this wake survey technique, feel free to check out this paper we wrote on this topic. The reference, again, is on the right of your screen.
All right, so there you have it. Hopefully now you're comfortable with what a wind tunnel is and how we can use it to acquire data for a scaled down version of an aircraft to obtain aerodynamic force and moment data. Now, in our very next video, we are going to look at how we can take the data that we just acquired and then transform and reduce it into something that's more representative for a full-scale free flight aircraft. So I think with that being said, this is probably a good spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. Surprisingly, if you just scroll a little ways down and click on that subscribe button, it really does help me continue making these videos. And remember, the new videos come out every Monday, so I hope you'll join us at one of these future discussions and we can all learn something new together. So until I talk to you again, I think I'm going to sign off. Talk to you later. Bye.